All right, here we go. Excuse me. Okay.
When the net force...
Nope, what are you reading?
Newton's first law. When the net force on an object is zero, an object that is already at rest will remain at rest, and an object that is already in motion will move with consistent velocity in a straight line. The above is a statement of Newton's first law. It is easy to parrot back on a test.
Stop. What does parrot mean? I can't hear you. Say it.
Copy.
Yeah. Yeah, copy or repeat, right?
Yeah.
Okay. Parrot.
Parrot back on a test, but it is quite different to truly understand what it means. At the rest part is easy for most people to understand. For example, a book at rest on top of a table will remain there until someone picks it up. The move with the consistent velocity part is a bit trickier. This part of Newton's first law says that the force is not required for an object to move with consistent velocity. Constant velocity. You might be thinking
to
yourself that this contradicts your everyday experiences. Clearly, you must keep pushing or pulling on an object like a chair to keep it moving, or else it will slow down and stop right. The key here is that Newton's first law is about the net force on the object while you are pushing the chair to keep it moving. There may also be other objects interacting with the chair, and thus other forces acting on the chair. In the case of the chair, there is also a force of friction from the floor which acts on the chair in opposite directions of your push. If it was sliding across the floor, you would have to push on. You would need to push on the chair to oppose
Good job.
friction and keep the chair moving at consistent velocity.
Nope. At
constant velocity.
Good. Okay, so let's read.
Based on Newton's first law, how does the strength of the force you exert on the chair compare to the strength of the frictional force exerted by the floor on the chair?
Okay, based on Newton's first law, how does the strength of the force you exert on the chair compare to the friction exerted by the floor on the chair? What's the answer?
They are equal. Newton's first law says that if the chair is moving at consistent velocity, the net force...
At what?
At constant velocity, the net force on the chair must be zero. Therefore, your push forward and the friction backward must be the same. No, the net force...
Nope. Okay. So, right, they are equal. Right? See, like here, look. Clearly, you must keep pushing or pulling on an object like a chair to keep it moving. Read that part.
Clearly, you must keep pushing or pulling on the object like a chair to keep it moving, or else it will slow down and stop. Right.
Key here.
The key here is that Newton's first law is about the net force on the object while you are pushing the chair to keep it moving. There may also be another object interacting with the chair and thus other forces acting on the chair. In the case of the chair, there is also a force of friction from the floor which acts on the chair in the opposite direction of your push. If a chair was lying across the floor, you would need to push on the chair to oppose friction and keep the chair moving at constant velocity.
Okay, so the friction is what causes it to slow down if you push it, right? All right, so here, based on Newton's first law, how does the strength of the force you exert on the chair compare to the strength of the frictional force exerted by the floor on the chair? Well, it just said they're equal, right?
Yeah.
Right?
Yeah.
Okay, so right, they are equal. Right
Yeah. They are equal.
Yep. Good. Okay. That's beautiful. This L should be extended all the way to the bottom, okay? Otherwise, very good writing, very neat. They are equal, okay? The net force of the chair must be 0. Net force equals 0.
Yeah.
Right here. Net force equals
0.
Just do the equal sign 0 and then do 0, okay?
Mm-hmm.
Net force equals 0, right here. Net force. Next time, net force is 2 words, not 1, okay? See here?
Yeah.
Net force, okay?
Okay,
good. So now,
equals 0.
Yeah. Space it properly, okay? Good. Now. Good. Good. Now, suppose.
Suppose instead the chair was lying across the ice.
Stop. So if it's ice, friction is less, right? So then that means, go ahead, so that
there was essentially no friction force exerted on the chair. Would you have to push on the chair to keep it sliding?
No, because there's no friction.
Yeah.
So no, because there is no friction.
Yeah.
No,
there is no friction.
No, comma.
Yeah.
No, comma. There is no friction.
Yeah. Comma. There is no friction.
Yep. It's good.
Yeah.
E-R-E. Now, E. Now, space is?
Is.
No.
No.
Do you know spell friction? It's right there.
Friction.
Look, right here. Look. Friction's right here. Not right here, look.
Oh, yeah.
There's no friction.
Friction. No.
Good. Okay, good. We're almost done. Okay. Okay.
Suppose a spacecraft out in deep space, far away from other objects, turns on its rockets until it reaches a speed of 10,000 meters per hour.
Nope.
Meters per second. At which point the rockets are shut off. What will happen to the motion of the ship after the spacecraft after the rockets are shut off?
Okay. But they shut off the rockets.
Mm-hmm. They shut off the.
They shut off the rockets. Yeah. Watch.
Shut.
There you go. Here. Ready?
Mhm.
Write this down.
Yeah. Mhm. They.
You see it?
Yeah.
Okay. Do it word by word so you learn, okay?
Mhm.
Yep. Good. Get ready for swimming, Abby. Bring me my phone, please. Thank you. Good. Okay. So then the answer is here, right? No force acting on ship will remain at what? What's the speed?
10,000 meters per second.
Good job. Very good. You all right?
I did on instead of no.
It should be on.
No force acting on ship.
Oh, yeah. Okay. Good job. You're pretty money.